Hello, everyone. Welcome to our bi-monthly Tech Talk. I'm just going to allow for another minute for people who are waiting on to join in, and then we can start briefly. Okay. Hi, everyone. Welcome for our regulars, and good to have some newcomers who have joined us for the first time. I will take a couple of minutes to introduce our tech partners from SFT Canada. So, hi, I'm Rajneesh. I head the strategy at Treadwell, while we have Toufic from SFT, who is the Chief Operating Officer at SFTec. And we also have Ahmed, who's the Senior Structural Researcher. In today's webinar, we will cover our Enviro range, which is our rebars, FRP rebars slash SFT bars, and we will cover the used case, the problem statement, comparison between different standard, whether they are AS5204, MRTS271, or CSA 807. After that, we will probably also try and discuss very high level how to design one of a structure with FRP. So without taking much time, we will probably start. So one of the reasons people ask about FRP rebars is what's the advantage? Now, I like to start this with a problem. Given the topographical, geographical location of Australia or other countries which is susceptible to moisture, water, the structures are faced with corrosion problems that basically reduce its design life because the corrosion in the rebars or the reinforcement makes it less usable over a period of time and reduce them. If we break it down into numbers, as per research papers, about 2.5 trillion USD is spent yearly on repair and maintenance of conventional steel reinforced concrete infrastructure. And this is a similar case between Australia, Canada, US, and other countries. Canada alone is estimated to spend about 900 billion each year, while in Australia, there are no current dollar value, but through CSIRO and other research uh, organization, we get to know that the figure lies between 3.5 to 5.2% of the total GDP of Australia that is spent on corrosion repairs, which, if we just do a quick calculation, is about 78 to 85 billion dollars. Now, how are FRP rebars made? Just like other FRP products or GFRP products, they are made of two high-level materials, which is the reinforcement, which can be glass, carbon, aramid, or basalt, and the matrix is resin, which can be vinyl ester and epoxy. They are used in a process called pultrusion, which is very similar to extrusion, where the glass fibers are very simply impregnated by the resin of choice, and then they are passed through a heated tool, which in this case would be a round shape, and through heat, the curing happens, and after that, the thermoset is actually formed. Certain advantages of rebars: it's got a longer service life. In cases it's been proven to actually surpass 80 to 100 years design life. It's improved durability in harsh marine environments. It's greater tensile strength compared to steel. There are weight savings. Depending on the size, FRP rebars can be one-fifth to the weight of steel. They are RF and electrical neutral, which means you don't have to invest in post manufacture earthing and bonding. And also, they do not offer any sort of disturbance in terms of magnetic or RF transparency. Further, these days, everyone is really keen to know about the carbon footprint and the sustainability because of the less energy consuming nature of these products as well as the lightweight nature. They do offer a 35 to 45% less carbon footprint. This can be attributed to lower logistical costs, manufacturing costs, and even installation cost. In certain cases, which probably can be structural, non-structural, but mostly non-structural because it's non-corrosive, one can even get away with a lesser concrete, but it needs to be designed for. Ahmed, I would probably leave it to you because the rest part is more technical, so I'd be happy if you want to run the next few slides.
Thank you, Rajneesh. Good morning, good night, everyone, based where you are. And thank you for joining today for a TikTok Tuesday session. My name is Ahmed Elbady. I'm Senior Structural Researcher at SFTec Canada. Today, I will discuss FRP reinforcement and its application in infrastructure projects. Specifically, we will cover the corrosion challenges affecting reinforced concrete structures, also the benefits of FRP bars, the relevant standards and specifications used in Canada and Australia, and finally, a case study comparing traditional steel reinforcement with GFRP reinforcement.
Ahmed, could you please move the slides as well to the relevant sections? Thanks.
Okay. Today, one of the foremost challenges facing reinforced concrete infrastructures is corrosion of steel reinforcement. When the bars exposed to chlorides or moisture or aggressive environmental conditions, the corrosion begins to occur. As steel corrodes, it expands in volume, which causes internal pressure within the concrete, the cracking of the concrete cover, and eventually spalling and structural deterioration. This issue, particularly in structures such as bridge deck slabs exposed to the icing salts, marine structures, wastewater facilities, and in general infrastructure projects. Corrosion is not only a technical issue, but also it's a major economical challenge worldwide. Current studies estimate that the global cost of corrosion exceeds $2.5 trillion annually for conventional steel reinforcement only. The cost of maintenance and repair estimated at over $100 billion per year. This cost include inspection, repair, and rehabilitation, and in many cases, complete replacement of structures. This is clearly shows that improving durability is not just an engineering target, but also an economic necessity. From the global perspective, corrosion costs present approximately 3.5 to 5.2% of the world GDP. For example, in Australia, the corrosion damage costs about $78 billion per year. In New Zealand, also, the annual cost is approximately $16 billion. However, current studies show that implementing effective corrosion prevention bars, it's possible to save 15 to 35% of these costs. One of the most effective solutions is the use of non-corrosive bars, such as FRP bars, which can eliminate corrosion problems completely. FRP bars is a composite material made from two main components. The first component is the fibers, which provide the strength and the stiffness for the bars. These fibers can made from different materials such as glass, carbon, armide, and basalt. The second component is the resin matrix, which blends the fibers together and protects them from the environmental exposure conditions. FRP bars are typically produced using a process called pultrusion, where fibers are pulled through a resin path and then through a heated die to form the final shape of the bars. This process allows for a high tensile strength and consistent quality. FRP bars offers several advantages compared to traditional reinforcement. First and most important, FRP bars non-corrosive materials. This means they can significantly increase the surface life of structures and expand the life cycle, especially in harsh environmental conditions. Also, FRP bars can provide high tensile strength compared to steel, much lower weight, typically about one quarter of the steel, and superior resistance to chemical exposure, and finally neutral to chemical electrical and magnetic disturbances. In addition, FRP bars also can contribute to lower environmental impact through reduced the maintenance and longer surface life. These advantages make FRP reinforcement particularly the attractive and most effective solution for bridges, marine structures, and infrastructure projects exposed to harsh environments. Now, we will delve into the second part of my presentation, FRP standards and specifications. As the use of FRP reinforcement increases worldwide, it becomes essential to have a clear standards and specification to ensure the safety and also the quality. In this presentation, we will focus on three key specifications used in Canada and Australia: CSA S807 in Canada, AS5204 in Australia, and MRTS271, which used in Queensland for transportation infrastructure projects. These standards mainly for different are mainly for different purposes. CSA S807 is primarily a material specification, which means that which defines how FRP bars must be manufactured and tested and how it can be certified. ASF204 defines the requirements of FRP reinforcing bars in Australia, including the mechanical properties and also durability performance. And finally, for MRTS271 is a project specification, which defines how FRP reinforcement should be used in transportation infrastructure projects. Together, all of these specifications ensure both product quality and proper application. We can summarize the relationship between these documents as shown in this slide. For material qualification is governed by CSA 807 in Canada and the same AS5204 in Australia. These standards define the mechanical properties, durability performance, and testing procedures. And once the material is qualified, MRTS governs how the material can be implemented in infrastructure projects, including installation and inspection requirements. So we have two main questions for if you have the questions how FRP must be manufactured and tested, you can use CSA S807 in Canada and the same AS5204 in Australia. But if you have the question how FRP must be used in transport project and infrastructure projects, you should use project specification for MRTS 271. For firstly, we will start with CSA S807 is a Canadian specification for fiber reinforced polymers used in construction and certification of materials. The main focus of this standards is the material characterization and quality control. Means that how we can test the bars, how many lots we need to use to test to can qualify and certify these bars, because if we take a look on CSA 07, we will see separate columns for manufacturer how to can certify their bars per lot, per bar size, per each diameter and everything. Okay, so for the main purpose of this specification, it is a material specification for FRP bars, tendons, grids, and shapes used in constructions. And also CSA S807 is developed by CSA Group in Canada, and the main focus and the main scope of this specification for the manufacturing, testing, and certification of FRP bars. The main contents of this specification: mechanical properties, durability requirements, manufacturing quality control, and how we can how we can get the acceptance criteria for FRP bars. And the other side for AS5204, as I told, is an Australian specification for FRP reinforcing bars. These standards focus on ensuring that FRP bars meet the performance requirements needed for infrastructure applications in Australia. And the main scope of this part is of this specification for manufacturing, testing, and infrastructure projects. Also, the main contents of this specification: mechanical durability, quality control, and certification and traceability, and also bar geometry and surface deformation. Here we can see both CSA 807 and AS5205 include extensive testing requirements. Both specifications have the same testing requirements. So in this point, because we have a lot of question specifically in this point, if we are certified with SA807, it's good for us. Yes, because the both specification includes the same testing requirements. Okay, why we need to do this test again if we have the same requirements? And it should be mentioned that AS5204 based on CS807 and also STM7957 and STM8505. These tests also evaluate several important properties of FRP bars, including three main categories: physical properties, mechanical properties, and durability properties. For physical properties, it include glass transition temperature, cure ratio, water absorption, fiber content, FTIR. Also, for mechanical properties, we have tensile strengths or tensile properties, interlaminar shear strengths, transverse shear strengths, and bond strengths. And finally, for durability properties, we have alkaline resistance with load and without load in harsh environmental condition, which in the bars exposure to alkaline solution for 3 months at 60 degree for 3 months. And we have two types of this test: without load and with load. Also, it should be mentioned that the physical properties, it is the primary results that can give us the target or the trend of the bars. If we have some bars and we need to judge for these bars, we need primarily to do the physical properties and then complete with mechanical and durability properties. Finally, SA807 make focus on material characterization, while AS5204 emphasizes long-term durability in infrastructure environments. Here in this slides, I get screenshots from the specification from AS5204 and also from SA807. We can see here, we can see all the property and the test requirements and the test methods for each property, and also the specified limit for each test. You can see as example for fiber content, the test methods ASTM D3171, and we have the same in S807, and the fiber content should be more than 75% of the weight, and also we have this percent in S807. In conclusion, we don't have any differences between AS5204 and CSA S807. It has the same standard, the same test methods, the same values. So we can depend on one specification to can specified or to can qualify the GFRP bars. Also, another example, we have here the guaranteed tensile strength of FRP bars around 1000 megapascal for number from 6 millimeter to 22 millimeter, and up to 20 millimeter for bar number 6. And for number 758, we have also the tensile strength from 800 to 900 megapascal. Also, this one for, as I mentioned, for some screenshots from S807, we have also the same specified limits, the same test methods, and we have another columns specify for qualification test how many tests is required to qualify these bars for cross section for each property, and also for manufacturer how many tests need to qualify and certify the bars. Now for MRTS 271, it's another document. It's a specification used by Queensland Department of Transport and Main Roads. Unlike the previous standards, this specification focus on project implementation. It defines requirements for approval FRP products, installation procedures, handling procedures, and storage procedures, and finally inspections requirements. For MRTS 271, we can see here also screenshot from this specification. It should only mention that in this screenshot, we can take a look for the tensile strength for straight bars shall be exceed 1,200 megapascal for bar diameter number 12 with bar number 4. If we remembered, we have lower value for both Canadian for SA S807 and AS5024. We will see here for Queensland specification, it's have more restrictions for the guaranteed tensile strength. Before it was 1,000, here it 1,200. So we need to make attention or take attention for which specification or which standards we used, because we need to meet the requirements of each one. But it should also mention that this specification depends on the testing requirements for S807 and also the document design for S806. So the design in Queensland depends on the same design code in Canada, S806. And also we have some additional testing requirements as creep density and fatigue strength. Now, I'll present a case study from one of our projects. Actually, I want to take a time to and spend more time to explain how we can design any infrastructure projects from scratch to the final stage and how we can check serviceability, how we can check ultimate state and everything. But due to the limit time, I prefer to prepare another webinar and go in deep details in design of these structures, and mainly this webinar for engineers and for everyone wants to know about how we can design with FRP bars. Also, we have many webinars at our website, SFTec website. We have webinars on many and different structures on how we design with FRP bars, from loads, from design, from check serviceability and everything. But now I will get a brief comparison between for one of our project to demonstrate the practical use of FRP reinforcement involving the design of retaining wall of one infrastructure applications. The main target, as I mentioned, is to compare the performance of traditional steel reinforcement compared to GFRP reinforcement. The retaining wall design uses the following parameters. For concrete strength, we use the compressive strength of 28 megapascal. For steel strength, steel reinforcement, it has a yield strength as 412 megapascal, and the GFRP reinforcement, the ultimate strength of GFRP reinforcement is approximately 1,000 megapascal. The design of this application follows the ACI design approach for FRP concrete reinforced concrete structures, ACI 440.11 for 2022. This slides shows the reinforcements layout for both slides and GFRP reinforcement. In this slide, we present the steel reinforcement we can see in these slides, due to the different mechanical properties of FRP materials, the reinforcement spacing and the bar sizes may differ slightly from those used steel reinforcement. However, the structural performance requirements are fully satisfied. We can see here also the all check serviceability for GFRP bars and how we can check the serviceability. But as I mentioned, we will perform another webinar in deep details for the design of these applications. And finally, we can see here the reinforcement of GFRP bars and the difference between both design. And finally, this slide compares the total reinforcement quantities required for steel and GFRP reinforcement. The results demonstrate that GFRP reinforcement can provide a competitive and durable alternative to steel reinforcement, particularly in environmental conditions where corrosion is a big concern. And also, as I mentioned, it is only for we cannot make the cost based on the cost of the material, but as I mentioned, we have cost of repair, of reputation, and everything. Finally, thank you very much for your time and attention, and I hope to present another presentation in deep details for specific practical applications and how we can design these applications. Thank you.
Thanks, Ahmed. That was pretty good. As we said, in the next coming weeks, we'll probably do a standalone webinar on the technical part of designing structures, such as a retaining wall or a seawall, where you can probably take all the time to go through the nuances and nitty-gritties. We'll probably allow for some time to take any questions if there are, and we'll try to answer them.
As I mentioned, Rajneesh, this presentation for general audience on how to know about GFRP bars and this simple comparison between GFRP bars and steel. But the other webinar will go in deep details for design, and the audience should be specific in the design for engineers and to how to expand the knowledge of how we can design with GFRP bars.
Perfect. So we have, Ahmed, can you see the Q&A window?
Yes.
Yeah. About the
First,
bent bars, the bars cannot be bent on site yet. The technology is not yet uh, accomplished and or approved and tested. But all the bent bars can be manufactured based on specs. Yeah, there's no problem to have them ready for you and sent to you.
I will add something. Can I add something, Tofik, for this
Of course.
point? Yeah. For any project we received, we prepare a full shop drawing, including the bent parts and everything about the parts. So the parts that we that received for in the site, it include everything with the bar mark and everything that you don't need to bend the parts in the inside. And specifically for this point, we can bend the bars inside, but nowadays there are current research on a new reason called the thermoplastic reason. With new bars, these bars will give advantages to bend the bars inside. But nowadays this bars under testing, and in the future will involve and in the upcoming codes.
There is a
So
question which is to do with the ductility compared to steel, including stress strain curve and ensuring for ductile failure.
yeah. We all know, or we know that steel is a ductile material, but FRP bars not ductile. It's linear elastic behavior until failure. But for this, not issue for this point or for this aspect, FRP codes take consideration to integrate that there is no ductility with FRP bars. So in for FRP design, we have we design on compression failure, not tension failure as steel. So we for steel, I know that the critical failure is a tension failure, but for GFRP bars, the critical failure is a compression failure, and the codes take a lot and many factors of safety to ensure that the FRP bars achieved and meet the requirements of FRP codes due to the ultimate and serviceability requirements.
How is the design performance compared when designed to Eurocode 2 versus ACI 440?
Okay. For design performance compared to Eurocode, as I mentioned, all of FRP codes has the main assumption of design for FRP parts, but there is some difference, including the ultimate strain of concrete, the assumption of mode of failure on and how we can adjust for the failure, its compression failure or tension failure. But is Eurocode, SI, CSA, and any FRP codes has the same assumption. So if you know the steps of design with SI, you can also design with Eurocode with a little change in the abbreviation and the equation, but it's the same and with the same concept.
All those codes are first degree cousins. Nobody can reinvent the wheel at the end of the day.
What is the cost difference compared to the conventional bars? As I mentioned, if we want to discuss the cost, we don't only make the cost for the material. We need to cost for short term and long term. Okay, so for material, uh, in some application it's a comparable, and some application also FRP bars have lower quantities compared to steel, and also in another applications the FRP bars have some more quantities compared to steel. But by the end of the day, we cannot judge for the cost on the material, but we need also to see the cost of repair, of the corrosion, and of the replacement of total structures. And as I mentioned in the presentation previously, I mentioned the cost of repair. It's very high, and if we need to compare the cost, we need to compare the cost in short term and long term. For long term, the FRP parts is superior compared to steel. For short term, for some application, it's the same. For some application, FRP parts is more. For some application, also FRP is lower, depend on the requirements of this application.
It's very similar to every other FRP application where probably to get a good sense, one doesn't really need to just take the material cost, but rather have an overarching view of the project cost, including the installation cost and the design life advantages that the FRP offers. So broadly, let's say a structure which has a 50-year design life with a conventional material versus with FRP as embedded reinforcement, which can, exceed up to 80 years. So there are benefits in the long term, if that answers your question. I think this is, Ahmed, an interesting one. The elastic modulus of FRP is significantly smaller than steel. Will that lead to bigger crack widths in concrete, which accelerates the corrosion of concrete itself?
Okay. This is very, very good points and very good questions. Okay. We have two aspects when we design with FRP bars. We design FRP bars under ultimate state and under service state. For ultimate state, FRP bars can be more 3 or 4 times compared to steel. Okay, but to 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 be sure that we have meets the requirements for the second part for service states, we have a check serviceability for FRP bars due to, as you mentioned, with that there's the elastic modulus of FRP bars is small, so there is a high restrictions in FRP codes. Due to the serviceability, and you know that when we design, we don't have any problem with the ultimate state. We only the state for the serviceability, including deflection and the crack width. So for this point, we have in FRB codes, we have a high level of limits to be sure that the lower modulus classes of FRB bars make the serviceability and the crack width in the end of the day will be safe, and also we increase the bars using FRP due to make the serviceability safe by the end of the day.
Thanks, Ahmed. We've tried to answer some questions. The rest that we haven't been able to, I and Ahmed will work on that, and we can send it to you later on during the day or the next couple of days. But Ahmed, let's probably plan for another in-depth webinar in the next coming weeks, and we'll announce that to our followers very shortly.
Maybe we can collect
Agree.
those
Yes.
questions to send the answers prior also. It would be good. Thank you.
Yes. Thank you so much, everyone.
Actually, Rajneesh, I see very, very good questions in the chat, but I make a quick response, but I will collect all of these questions and get a clear and detailed response with references from code and everything to make everything clearly for the audience.
Perfect. Sounds like a plan. Thank you, everyone.
Thank you, everybody. Thank you, Treadwell, for organizing this.
Thank
Thanks.
you.
Thanks, Toufic. Thanks,
Thank you.
Ahmed.
Thank you.
Bye-bye.